this video is going to look at the introduction of carboxylic acids. Now, in this chapter, we're going to be looking at a lot of new functional groups, and compared to aldehydes and ketones, we actually have groups that can be replaced by a nucleophile. So in carboxylic acid, esters, acyl or acid chlorides, as well as amides, we now have a group that could be considered a leaving group under the correct conditions. When we look back at aldehydes and ketones, we had a hydrogen and an R group or another carbon that could not ever be substituted because we would create a very poor leaving group. So the arrows we're going to draw in this chapter are very similar to the ones we've seen in the ketone and aldehyde chapter, as well as in the alpha hydrogen chapter, but there's another level of complexity because we can have two equivalents add. The first one removing the carbonyl double bond, and then the second one removing your new leaving group. Let's talk a little bit about these functional groups first. The main one for this chapter is the carboxylic group. We can see those written in lots of different ways where you have the entire group written out versus just your shorthand, or even shorter, combining the two oxygens. Naming for carboxylic acids is very straightforward. You're taking your ANE alkane ending and turning into OIC acid, oic acid. So here I have a 5-carbon carboxylic acid, so it would be pentanoic acid as I add another carbon, hexanoic and propanoic. Notice here, no numbers. When you're naming carboxylic acids, your number 1 carbon is going to be the carbon of your carbonyl group. So you can number from right to left here. We also talk about these positions, alpha, beta, gamma, delta, epsilon. You already know this because you covered the alpha carbon chapter first. But know that we're saying that the alpha carbon would be right next door, right? That chemistry doesn't change for these groups. So here you can have some practice trying to go through these. Here we have an ether, so we have a 2-methoxybutanoic acid. Here we have a bromo on the 3 position, and on the bottom we have our chloro on the 4 position. So nothing really changes outside of our ending here. Boiling point is an interesting topic when we talk about these carboxylic acid derivatives. Most students want to look at the more complex, the higher the boiling point, but there's a couple other forces at play here, mostly hydrogen bonding. So our first groups having the highest boiling point are going to be our amides, our carboxylic acids, then our alcohols because of hydrogen bonding, and then we're mostly looking at dipole-dipole forces, and I would say that acid chlorides and ketones are going to be pretty close. Your esters are going to be surprisingly at the end, and then your ethers will be at the end. And here are your boiling points again. You can see 4 and 5 really close, 4, 5, and 6 really. And so I would say that you need to make sure you're okay with alcohols, acids, and amides being the highest, while your other groups are all going to be pretty low. So this would be your sort of hierarchy, with your amides, carboxylic acids, and alcohols being much greater. Esters, acids, chlorides, ketones, aldehydes, all pretty close. Why is this? You can think about the H bonding, hydrogen bonding, as well as the specific dipole-dipole interactions that can come with amides and carbonyl groups. So for the main reaction in this chapter, we're going to be looking at nucleophilic acyl substitution, where our nucleophile is going to come in. We know that this arrow is going to push electrons out onto the oxygen. At this point, you have your tetrahedral intermediate. Now at this point, you can look at your two possibilities. What's going to be happier having that negative charge? Oxygen or Y, which you're going to turn into your leaving group. If that Y group is a good leaving group, carbonyl is going to push those electrons back down and reform. Now at this point, you know that depending on what Z is, you could have made an aldehyde or a ketone, meaning that this can then react just like a normal aldehyde and ketone would. If we have a weaker base, we can have our nucleophile come in, kick electrons out. At this point, if oxygen is more upset than the Z minus, we can have the electrons pushed down, and rather than our Y group leave, our nucleophile that was just added is going to be eliminated, and you'll reform your reactants. So think about what's going to be happier with the negative charge, right? That's saying that you have your weakest base being eliminated. So if your incoming nucleophile, or your Z, is a weaker base than the base in the reactant, your Y, the reactants will be reformed. So here notice that in both of these scenarios we're saying that the negative charge is not going to stay on oxygen. So you shouldn't see any alcohols as a result of these initial reactions, because we're saying either oxygen's kicking out Y or it's kicking out Z. So that's the main difference from our reactions in the aldehydes and ketones. So when we're a stronger base, we can have our nucleophile come in, push electrons out. Now our leaving group can leave. So since it's a weaker base, Y can be eliminated, and you now have made a new compound or a new product. Take a look at these quick examples. Here we have an acid chloride and an ester. And what I want you to think about here is, if one of these reactions happens, will the other one? We have a nucleophile here. Our methoxide ion can come in and replace the chlorine. We've gone from an acid chloride to an ester. And think about stability here, right? We've gone from something more reactive to less reactive. That means that we are not going to be able to displace that methoxide group with the chlorine. Remember, which is the weaker base? Who's happier with the negative charge? Methoxide's pretty upset about it. Chlorine's going to hold on to that negative charge and be okay with having it. So you can always convert to a less reactive, but you're going to have trouble converting to a more reactive species. First reaction I want to talk about is the reaction with an ester with the hydride ion. So lithium aluminum hydride you saw in the ketones and aldehydes chapter. So I like to start out with one that has similar properties, and you can see the small differences here. I'm starting with an ester. What this is actually going to turn into is an alcohol, specifically because we are adding multiple hydrogens. Okay, so this is not turning into an alcohol during the part of this process. The alcohol is being added from your hydronium ion. Notice here we have two pieces. You can see that we still have our 3-carbon chain, showing you that our 1-propanol, that oxygen is coming from the carbonyl oxygen, and our methanol is coming from the ester piece. So let's look at how these products form. We're going to start off by drawing the same arrows that we would with an aldehyde and ketone, coming from between the bond between hydrogen and aluminum. We're going to push those electrons towards the electrophilic carbon, pushing electrons out onto the oxygen. At this point, we can say what oxygen is going to be more okay with that negative charge, our carbonyl or our ester. So our methoxide group is going to have the oxygen and a methyl group to help stabilize the negative charge. The top oxygen is just by itself. So we actually can make a weaker base by kicking that out. Notice here we've created an aldehyde, meaning that we can undergo a second addition of lithium aluminum hydride. Both in the first step and this step, it doesn't matter what species the lithium aluminum hydride finds. Remember, it's always looking for a carbonyl group. So our arrows for step 1 and step 3 are going to be the same. You're going to still have your electrons come in, push at the electrophilic carbon, out onto the oxygen. At this point, you have a negative charge on your oxygen, which can then work up into a primary alcohol. And you want to remember your other piece, that this methoxide group that was our leaving group can also pick up a hydrogen from the acid workup. You're going to add 2 equivalents of your lithium aluminum hydride, turning this into an primary alcohol. If you have an amide, you can still use lithium aluminum hydride. Here we're adding 2 hydrogens to our carbonyl group, giving us from an amide all the way to an amine. And remember, the arrows for all these are going to be very similar. Here I have another amide. We can still turn that into an amine. Here it's going to be a secondary amine versus a primary amine, so how many carbons are attached to the nitrogen, but still same steps. And some extra nomenclature questions for you to try.